Hi everyone, welcome back to Data Cadence. My name is Rahul. I work as a senior applied research scientist, and in today's video we are exploring a concept that's very fundamental yet incredibly powerful in the realm of support vector machines or SVMs, that is the kernel trick. Now you might be wondering, why is the kernel trick such a big deal and why you should care about it. Well, the kernel trick is one of the most important concepts that might seem abstract at first, but it plays a very crucial role in transforming how we approach complex classification problems. And understanding it can significantly enhance your ability to apply SVMs to a variety of real world data scenarios. So in this video, we are going to break down the kernel trick in detail, but we are not just going to skim through the surface. Our focus will be on understanding the intuition behind it, why it works, how it helps in making non-linearly separable data linearly separable, and finally how you can leverage it to improve your machine learning models. So without further ado, let's begin. So first, let's quickly review the basics of SVM. So SVMs are one of the most fundamental machine learning algorithms used for both classification as well as regression. Although a more common use case or the more frequent use case is classification, you would rarely find people using SVMs for regression, but yes, SVMs can also be used for regression. So that is one thing which you should keep in mind. And the goal of SVM is to find an optimal hyperplane that separates the different classes in the feature space. So if you were to consider a very simplistic example in two-dimensional space, so this is how the figure looks like. I'll just explain it. So you see that this particular data points is what is called the support vectors. So say you have two classes. One is marked by the circles in purple and the other one is the cross symbol in the blue color. And in this case, you see that this is the maximum marginum hyperplane that we are interested to find when we are performing an SVM on top of this particular data. And these axis parallel hyperplanes are called as the positive hyperplane, which separates the positive class from the negative class. And similarly, this is called as the negative hyperplane. And this particular gap between the positive and the negative hyperplane is what we call as the maximal margin. And these points which are closest to the particular maximum margin hyperplane are called as the support vectors. So just some terminology so that you are aware. And in a hard margin SVM or in a simplistic setting in an SVM, it assumes that the data is linearly separable. And what it means that we can separate the classes with a straight line. If we talk about a 2D, in a plane it becomes 3D. When it refers, I refer it to as a plane, I mean that the data is in 3-dimensional, or in general, if the data is in higher dimensional, we call it a hyperplane, and that's what we saw in this particular diagram above. Now the problem is with the non-linearly separable data, because in many of the real world scenarios, or actually in most of the real world scenarios, the data is not linearly separable. So for instance, imagine you have two classes which are arranged in concentric circles, and a straight line cannot really separate these two groups. That is pretty evident, and this is where the kernel trick sort of comes into play. So the kernel trick allows the SVM to operate in a higher dimensional space where the data might be linearly separable, even if it's not in the original feature space. And that's the whole idea behind the kernel trick. So we can use a feature transformation function called phi of x. And in the above case of say concentric circles, transforming the data into a higher dimensional space might make it possible to separate the classes with a particular hyperplane. So like I mentioned, the idea is to go from d dimensions to say d prime dimensions using the function say phi of x, and typically d prime is much larger than d. That is, you transform your data into a higher dimensional feature space where the data might be linearly separable, and that's the whole idea behind the kernel trick. Now this is typically achieved using a kernel function, and the kernel function is used to compute the dot product in the higher dimensional space directly without performing the actual transformation phi of x. And what that means is that you don't really need to explicitly find out this particular transformation function, that is phi of x. Instead, you can use a kernel function to do that particular similar computation for you. And the key point, like I mentioned, is that we don't need to know the explicit transformation function phi of x. We just need to know how to compute the kernel function, that is say k of xi and xj. And if phi of x is the transformation function, then the dot product in the higher dimensional space is phi of xi dot with the phi of xj. And just for your clarity, xi, when I say xi, it means the feature vector of the ith data point, and xj refers to the feature vector of the jth data points. And the kernel function gives you the dot product directly. So you might be wondering, how does the kernel function essentially give you the dot product between phi of xi and phi of xj? So you can derive this mathematically, but that would be out of the scope of this particular video and it would make the video unnecessarily lengthy. So I'm just leaving that one, but even if you take simple kernel functions like a linear or a polynomial kernel function, you can easily derive this particular thing and arrive at this particular conclusion. But this is what you need to know, that this particular kernel function avoids the need to explicitly compute phi x and work in the higher dimensional space. Now there are certain common kernel functions that you need to be aware about. So first one is the linear kernel. It's the simple dot product between xi and xj. Then you have the polynomial kernel, that is given as the dot product between xi and xj plus you add a constant and then raise it to the power of d, where like I mentioned, c is the constant and d is the degree of your polynomial. And then you do have a very popular generic purpose kernel, that is the RBF kernel. So you must have heard about this because this is a very good generic purpose kernel and works really well with non-linearly separable data in a generic case. And this is simply given as the exponent of negative gamma times xi minus xj to the squared, or the L2 norm of the xi minus xj. And gamma is basically a parameter that controls the spread of your particular kernel. And the important thing to note here is that there are also many domain specific kernels that work best with a particular domain. So say for example, if you're working in a medicine domain or in a finance domain or any other particular domain, so people have come up with the domain specific kernels that work really well with a particular kind of data. And this was an active area of research back then. People were trying to come up with their own kernel functions for their respective domains. And back then, this was one of the primary reasons for the popularity of SVMs, right? So to sum up this particular video, if we were to talk about the practical implications of the kernel trick, so using the kernel trick has several benefits. The first one is efficiency. So it avoids the computational cost of explicit transformations. The second one is flexibility. So it allows the SVMs to handle complex data structures. And finally, the performance, or the most important one. So it can improve the classification accuracy by transforming non-linearly separable problems into a linear separable ones in a higher dimensional space. So in summary, the kernel trick is a very clever method that enables SVMs to tackle non-linearly separable data by computing the dot products in a higher dimensional space without explicitly performing the transformation. And this is what makes SVM a versatile tool for a wide range of classification problems. And this is important to know for a day-to-day work scenario, as well as it's a very important interview question because it implies your understanding of SVMs and the kernel trick. And if you say that you have used SVM in one of your projects, how much do you know in depth about these concepts, which are very fundamental when it comes to SVM. So hopefully this video gave you some more insights and you learned something out of this. If you did, please consider pressing the like button. And if you are new to this channel, subscribe to this channel for more such content around interview prep, machine learning, and data science in general. So thank you so much for sticking till the end. I will see you in the next video. Until then, take care, stay safe, and keep learning.